Hello students, welcome to the lecture on basics of electrical and electronics engineering. Today we'll start the 13th session and continue with unit 3, fundamentals of AC circuits. Today we'll learn about alternators. Alternators are also called as AC generators. So we will be studying working principle of AC generator, construction details, main parts of an alternator, applications of AC generators, and ratings of alternators. To begin with, let us see the definition of an alternator. An alternator is an electrical machine that converts mechanical energy into electrical energy in the form of alternating current. It is also called as an alternating current generator. Hence, it gets the name as AC generator. So, basically, it is a machine which converts mechanical energy into electrical energy, where the output is in the form of alternating current. It works based on the principle of Faraday's laws of electromagnetic induction. So we have to recall Faraday's laws of electromagnetic induction. The Faraday's law states that whenever a conductor is placed in a varying magnetic field, an EMF is induced, and this induced EMF is equal to the rate of change of flux linkages. So both the laws are combined here. So the Faraday's first law states that whenever a conductor is placed in a varying magnetic field, then an EMF is induced. And the second law states that the amount of EMF induced is directly proportional to the rate of change of flux linking with the conductor. So together we can combine and understand it as whenever a conductor is placed in a varying magnetic field, an EMF is induced, and this induced EMF is equal to the rate of change of flux linkages. Now, if the conductor is provided with a closed path, then the induced EMF causes a current to flow through the conductor. Now, let us watch a video here to understand the concept better. ಇಲ್ಲ ಅದರಲ್ಲೇ ಬರುತ್ತೆ. ಅಲ್ಲ ವಿಡಿಯೋ ಬರೋದಿಲ್ವಾ? ಅಲ್ಲ ವಿಡಿಯೋದಲ್ಲಿ ಆಡಿಯೋ ಬರಲ್ವಾ? ಓಕೆ Okay, as you observe the video, you can understand electromagnetic induction. So you can see a bar magnet which is being moved to and fro away from an coil. So the right-hand rule here will give you the direction of the induced current. So they are the field magnets. In the air gap between the field magnets, the armature is placed. The ends of the armature is connected to slip rings and brushes are placed over the slip rings. The field magnets are concave in nature, so the field is radial in nature there. So that is the slip rings. So that is the brushes which are placed over the slip rings. Brushes collect the current from the armature winding and it is supplied to the external circuit. So here it is connected to a galvanometer. We have already studied the generation of AC. So you can observe that as the armature winding is rotated in the air gap, an EMF is induced. Since it is a closed path, because of the induced current, the galvanometer shows deflection. So when the armature winding is rotated in the field, it is going to cut the flux present in the air gap there. So according to Faraday's law, as the flux is being cut, an EMF is being induced, because of which a current is flowing in the galvanometer. You can observe the deflection of the galvanometer pointer. During one half turn, it is in one direction. During the other half turn, it is in the another direction, opposite direction. Thereby, it is clear that an AC is being generated. An alternating current is being generated. Observe the galvanometer along with the movement of the armature. Induced path, because of the induced current, the galvanometer shows deflection. So when it is rotated in the field, it is going to cut the flux conductor. You can observe is in one half is green in color, the other half is pink in color. The direction of the currents in these conductors and EMF is being induced, because of which a current is flowing in the galvanometer. You can observe the deflection of the galvanometer pointer. During one half turn, it is in one direction. During the other half turn, it is in the another direction. See the direction of the current shown by the animated movement of electrons. So when voltage is plotted against time, observe that for every half revolution, you are going to get a half cycle of AC wave here. Along with that, observe the galvanometer deflection too. Okay. So after watching that video, you might have recalled the Faraday's laws of electromagnetic induction and also how an AC current, alternating current is going to be generated. Now, let us come to the principle of operation of an alternator. Here, consider three identical coils A, B, and C placed on the rotor of a generator at an angular displacement of 120 degrees. Now, this constitutes a simple two-pole, three-phase alternator. So here you can observe here in this figure, this is a three-phase alternator here. There are three coils A, B, and C. You can observe here A, B, and C. So they each winding constitutes the phase winding. Now every winding has got two leads or terminals coming out, and finally we have to bring out only three terminals. So the three windings here can be connected either in star connection as shown here. We have already learned about star and delta connection. So here you can see it is star connected. The central point is called as the neutral, and three output lines are obtained here. Or it can be delta connected here, where the dissimilar ends of the windings are connected together here. And finally, three output terminals are going to be obtained outside. Now here, the three windings here are placed at an angle of 120 electrical degrees apart. So you can see here, if red represents one winding, say A winding, and yellow represents the B winding, and here the blue represents the C winding, let us say. Every winding has got two ends, and if we call that ends as A1, A2 of A winding, B1, B2 of B winding, C1 and C2 of the C winding. Now the three windings are placed 120 degrees apart. You can see here the three windings are placed 120 degrees apart, and A1, C1 and B1 are brought to a common point here. Now this winding is placed in a magnetic field. So we have the North Pole and the South Pole. So you can see here the end of the magnets are concave in nature, so that it will provide a radial magnetic field. So in this air gap between the magnets, the coils are going to be placed. So you can see another version here. This is the stator, and here are the three windings. A1, A2 is coil A, B1, B2 is coil B, C1, C2 is coil C. So the windings are placed here, and when the winding starts rotating, now this forms the rotor. This forms the rotor, while the magnets form the stationary part. Okay, so when the rotor starts rotating here, the magnetic field existing here in the air gap is being cut. So as the magnetic field is being cut, an EMF is going to be induced. So that induced EMF, you can see the one represented in red here is V1. Let us say V1 is the EMF induced by the coil A. V2 is the EMF induced by the coil B. V1 and V2 here. That is totally coil B. And V3 is the EMF induced by the coil C. So all the three coils are going to induce EMF, but you have to understand that if the direction of rotation of the rotors here, that is the conductors here, is taken to be anti-clockwise direction of rotation, then to begin with, the A conductor, the A coil is going to induce an EMF as shown by red here. Okay. After a lag of 120 degrees, the B coil is going to induce an EMF. So it is going to start here. You can observe here, this is corresponds to 120 degrees. And that is because the B coil is lagging 120 degrees behind the A coil. Thereby, the EMF during the rotation, the B coil is lagging behind the A coil by an angle of 120 degrees. Therefore, the EMF induced by the B coil is lagging by 120 degrees. So it is going to start here. You can observe here. And it goes on. Next, here observe the C coil. Now C coil with respect to anti-clockwise direction of rotation is behind A coil by 240 degrees. So this is 120 degrees. This is another 120 degrees. So totally it is behind the A coil, which is represented by the red vector here. It is totally 240 degrees behind the A coil. So that is represented by blue. So it is going to start here. So after 240 degrees. So this is 0, this is pi, 120 degree, 180 degrees. And here it is going to be 240 degrees. Okay. But since it is circular, the armature, the conductors are placed in a circular pattern. Now this is only an expanded wave diagram. So thereby you can see the continuation of these waves here too. Okay. Otherwise, since it is circular, it is not visible here. Since we are going to write a developed or an expanded wave diagram, you can see here the extension of these induced EMFs here. So what we have to understand here is the three EMFs which are going to be induced in case of a three-phase alternator lags each other by 120 degrees since the coils are placed 120 degrees electrically apart. Okay, so let us come back here. So each winding or coil is called as the phase. The voltage induced in each winding is called as the phase voltage. The angle between each phase voltage is called as the phase angle and is equal to 120 degrees. Now, these coils are rotating in a magnetic field in anti-clockwise direction with a velocity of omega radians per second. Now, AC voltages will be induced in these coils or phases as they cut the field flux during rotation. So here you can see this is the north pole and the south pole. In the air gap, the conductors are placed here. So the three phase is obtained by placing three coils here, three conductors here. The ends of the conductors are designated here. You can see R1, R2 is one conductor, Y1, Y2 here is another, B1, B2 is another conductor here. So there are only three conductors. The ends of the conductors are designated as R1 and R2. So when they are rotating in this air gap, they are cutting the flux, thereby an EMF is induced, and in a closed circuit, an induced current is going to flow. Okay. Now we have to learn the Fleming's right-hand rule. Now the Fleming had proposed two rules. One is the left-hand rule, which is used for motors, and another is the right-hand rule for the generators. Now since we are discussing about AC generators, we will learn the Fleming's right-hand rule. Now, according to the Fleming's right-hand rule, it says that when the thumb, the forefinger, and the middle finger of the right hand, so observe the hand here, the thumb, the forefinger means it is also the pointer or the index finger, the forefinger, and the middle finger here. When all the three fingers of the right hand are stretched to be perpendicular to each other. So each one must make an angle of 90 with the other. So you can observe here, the thumb is perpendicular to the forefinger. The forefinger is perpendicular to the middle finger, and the middle finger is perpendicular to the thumb. So when you stretch the three fingers of your right hand, the thumb, the forefinger, and the middle finger to be perpendicular to each other, then if the thumb represents the direction of movement of the conductor, the forefinger represents the direction of the magnetic field, then the middle finger represents the direction of the induced current. So you can observe here the field magnets. So in the air gap, we have the conductor placed here. These dotted lines are the magnetic lines of force, or it is also called as flux. And when you stretch the three fingers of your right hand and hold it such that the forefinger is in the direction of the flux, you can see the arrow mark here. So the forefinger is in the direction of the flux. The thumb finger is in the direction of motion of the conductor. How the conductor is moving, in which direction it is moving in the magnetic field, it is pointed in that direction. Then you can see that the middle finger gives the direction of current in the conductor. So this will be the direction of current. You can observe here, this is the direction of current. So let us watch a video here. Okay. Let us watch how a three-phase AC generator is going to work, and we will see the generation of three-phase EMF here. So you can see here there are a number of armature windings here. So if the more than one are there, you can call it as polyphase alternator. So you can see it produces voltage waves equal to the number of windings per phase. Thus, a polyphase system consists of numerous windings which are placed on the same axis but displaced from one another by an equal angle, which depends upon the number of phases. Since we are considering three phase, so the angle is going to be one complete rotation constitutes 360 degrees. Therefore, three phases means 360 divided by 3, that is equal to 120 degrees. So the windings are placed at 120 degrees apart. Or suppose if we are going to use more number of phases, say we are going to use 6 phases, then it is going to be 360 degrees divided by 6. So that will be equal to 30 degrees. Each angle is going to be 60 degrees. 360 degrees divided by 6. So it is each angle is going to be between the windings is going to be 60 degrees. So like this, it is displaced from one another by an equal angle which depends upon the number of phases. But three-phase alternators are widely preferred for transmitting large amount of power with less cost and high efficiency. So let us see the generation of three-phase EMF. So we can observe the three coils here. One is red, one is blue, another is green, displaced at 120 degrees apart. They are placed in a uniform magnetic field. So the ends of the coils are connected to slip rings and brushes are present over the slip rings. So between any two windings or phases, it is going to be 120 degrees apart. So it's 120 degrees apart. So it is rotating in the anti-clockwise direction. So the induced EMF is going to be, you can see how the wave is getting plotted. So EA1, A2 is the induced EMF of the red conductor that you see there. Then EB1, B2 is of the B phase. You can also call it as the RBY phase. And EC1, C2 is the induced EMF being generated by the C winding. Thus, the EMF induced in all the three are equal in magnitude and are of the same frequency. So it is given by the equations. A1, A2 is E naught sine omega t. B1, B2 is E naught sine omega t minus 2 pi by 3. That is minus 120 degrees. And EC1, C2 is given by E naught sine omega t minus 4 pi by 3. 4 pi by 3 means it is 240 degrees. By this equation, we know that it is lagging behind the R phase by 240 degrees. So it is showing the way different point of time at which they are attaining their peak values. With that video, we have been able to understand the generation of three-phase EMF as it happens in case of an alternator. Now let us understand the details of construction. Now before going to the actual constructional details of an alternator or the AC generator, one difference you have to understand between a DC generator and an AC generator. In case of a DC generator, the armature windings are rotating while the field windings are stationary. So this is the construction of a DC generator. You can observe here, these are the field poles on which the windings are placed. They constitute the field windings, and in the central place in the air gap here, the armature is going to be placed. So there is the armature core which has the slots, and in the slots the armature conductors are placed. Now so the armature is free to rotate here. So here what we see that is the armature windings are rotating, the field windings are stationary. Whereas in case of AC generators, you can observe here, it has got a rotating magnetic field. That is, the field windings are rotating while the armature windings are stationary. Here, this constitutes the armature winding. They are stationary, whereas the field winding here is rotating. The main parts of an alternator are, one is the stationary part called as the stator, and another is the rotating part called as the rotor. So here it is just a picture for you to understand. So this which is stationary and which is housed in a iron frame here is constituting the stator, and this part constitutes the rotor. This will rotate inside the stator here. So that is a rotor. Then that which rotates is the rotor. That which is stationary is the stator. Now the stator, it consists of a cast iron frame which supports the laminated armature core, having slots on its inner periphery for housing the three-phase winding. So you have to observe the figure here. Now this is a stator. Now this is the outer periphery, that is the outside. This is the inner periphery. So inside portion of the stator, you can observe there are a number of slots. A number of slots are present, and inside the slots you can see this is the conductors, coils or the wires that are going to be placed. So conductors are going to be placed inside the slots, and finally only 3 leads like this is going to be brought out. You can observe here 3 leads are brought out. Okay. Now this is a bigger stator here. You can observe how big it is. So this is the stator construction. Now it is supported on laminated armature core. Again, we have understood about why laminations are done. We have studied that in transformers. We are not going to use a single thick stator armature. it is going to be a number of laminations. A number of stampings of thin sizes are going to be stacked and riveted together. This is how a stator lamination is. Okay, stator. Now this is the stator slot where the conductor is going to be placed. This is called as the tooth of the stator. So the conductors are placed inside this slot. So they are firmly held there. Okay. And here you can see a number of small thin sections. This is the laminations. They are all bundled together or stacked together to make a big stator like this. See what you saw here. Can you see here? So a number of laminations are stacked together to form this stator. This is to reduce the recurrent losses. Okay. So this is another picture of a stator. So you can see here clearly how the slots are, and inside the slots, these are the conductors which are going to be placed. You can see here, this is the conductor which is going to be placed inside the slot. So the ends of the conductor are brought outside. Here you can see this is known as the overhang of the windings. So here further connections are going to be done. Next is the rotor. Now rotor is the rotating part of the AC generator. The field windings are placed on a rotating element called as the rotor. The rotor is of two types. One is salient or projecting pole type rotor, and another is smooth cylindrical type rotor. So you can see the construction of the salient pole here. So this is the inner periphery of the stator. Inside you can see conductors are placed. They form the armature winding here, or the stator winding. Now this is the salient pole. You can see these poles, north, south poles you can see here. They are projecting type of poles. So these are the poles. And on the poles here, you can see this, the field winding is going to be placed. The field winding is going to be energized by a DC supply here. So the field windings are placed on this. Since the portion is projecting like this, it is called as the projecting pole type, or it is also called as the salient type of rotor. Whereas in the cylindrical rotor, again, this is the stator. On the inner periphery, slots are present. Inside that, the conductors are placed. And here you can see some portion is left unslotted. Here, it forms the north pole. Similarly, here, it is not slotted here. That forms the south pole. And the rest of the area of the region is going to be slotted. And in the slots, the field winding is going to be placed. Now, since the construction here is cylindrical, you can see this, it's a smooth cylindrical in nature. This type of rotor is called as smooth cylindrical type rotor. Let us see the features of the salient pole type of rotor. It has got large number of alternate north and south poles bolted to it. See, either permanent magnets can be used in case of very small size of the alternators. But in case of large alternators, it is not advisable to use permanent magnets, and also very huge permanent magnets are not available. So it is electromagnets. So here a large number of north and south poles are bolted to it. The magnetic wheel is made of cast iron or steel, which is of good magnetic quality. So permeability must be very high. The magnetic poles are excited by a small DC generator mounted on the same shaft of the alternator. So the field windings which are placed on the rotor are excited, that is the supply to it is given by a small DC generator. Now this small DC generator is also mounted on the same shaft of the alternator. The air gap between the rotor and the stator is non-uniform because you can observe here, air gap here. When you come here at this point, the air gap between the rotor and the stator is very less. When you come at this point, you can observe the air gap is very large. Again here it is very small. So the air gap is non-uniform in case of a salient pole type of rotor. The air gap between rotor and stator is non-uniform. They have large diameters and short axial lengths. So huge diameters. The size of the machines, rotors are going to be very large. Now this type of rotors are used in low and medium speed alternators. And also they are mechanically weak because they are all projecting pole type, and when they are rotating, they are subjected to centrifugal forces and thereby they are mechanically weak. Now this is the construction of a salient pole type of rotor. So this is the armature winding. This is the poles here. You can see a number of poles are present here on which the windings are placed. You can observe here the windings, and the ends of the windings is connected to slip rings here, and DC supply is given as input here, and from the stator 3-phase supply is taken as the output. Next we'll understand the cylindrical type of rotor. Now this type of rotor consists of smooth and solid steel cylinder having slots along the outer periphery. So you can observe here, this is the outer periphery. Okay, so this is the outer periphery. So slots are present, and inside the slots the field coil is going to be placed. Now this unslotted portion here acts as the pole. This is one pole, this is another, this is another one, and this is the other. So this is a 4-pole rotor, you can see. Okay. 2 or 4 regions of the central polar areas are left unslotted. The central polar areas are surrounded by the field windings placed in the slots. The air gap between the rotor and the stator is uniform. So, see this figure here. You can observe here, this is the rotor, this is the stator. So, in case of a cylindrical rotor, you can see everywhere it is uniform here. See, whether it is here or here or here, the gap between the rotor and the stator is throughout, it is uniform in nature. So the gap between rotor and stator is uniform. They have small diameter and long axial lengths. This type of rotors are used in high-speed alternators. So because of the small diameter, they can run at high speeds. Okay, and they are mechanically strong. So this is the stamping. So number of stampings or laminations will again be stacked together to form the cylindrical rotor. So here you can see the DC excitation given to the field winding. Now let us compare salient pole motor and cylindrical type of motor. In salient pole, the poles are projecting out from the surface, whereas in case of cylindrical type, the unslotted portion of the cylinder acts as the poles, and hence there are no projecting poles. In salient, the air gap is non-uniform, whereas in smooth cylindrical, the air gap is uniform. Salient poles have large diameter and small axial length, whereas smooth cylindrical have small diameter and large axial length. Salient poles are mechanically weak, whereas cylindrical type is mechanically robust. That is, it is strong. Salient poles are preferred for slow speed alternators, whereas smooth cylindrical is preferred for high speed alternators. The prime movers used for salient poles are water turbines and IC engines, whereas for smooth cylindrical type, the prime movers used are steam turbines and electric motors. For the same rating, the size of a salient pole is smaller than the cylindrical type, whereas it is for the same rating, the size is higher or bigger than that of a salient pole type of motor. So this is just a sectional view of an alternator. So this is how the core laminations are. So a number of such pieces will be joined together through dovetailed joints. You can see here, they can be attached together. So this is the overall frame of the machine. This is the central shaft. Okay. On that, the rotors, you can see the projecting poles here that is present. And there are windings placed on these poles, which constitutes the field winding. Here is the armature core, and in the slots, the armature windings are placed. The outer frame is called as the yoke or the frame, and this extended portion here constitutes the pole shoes. So this is the stator and this is the rotor. Now, having understood the constructional details of an alternator, let us go through the operation or the working of the alternator. We have already seen the video, so we have understood how it operates. Let us go through the points. So DC supply is given to the rotor winding through slip rings and brush arrangement. The armature conductors are stationary and the field magnets rotate, are rotary in nature. When the rotor is rotated by the prime mover, the stator winding or the armature conductors are cut by the magnetic flux of the rotor poles. So here, the rotor poles are also carrying windings. When it is energized, it is also going to set up a magnetic field, because we know that any current carrying conductor sets up a magnetic field around itself. So when the rotor rotates, okay, the magnetic flux is going to be cut, and thereby an EMF is induced. The armature conductors are cut by the magnetic flux of the rotor poles, and hence an EMF is induced in the armature conductors. Because the rotor poles are alternately north and south, they induce an alternating EMF in the stator conductors. Due to this induced EMF, a current starts to flow through the armature conductors. For each phase winding, there is a definite time lag of 120 degrees due to the spaced displacement arrangement of 120 degrees between the phase windings. So we have seen the pictures there where the three coils A, B and C were spaced at 120 degrees apart. The three-phase power flows out of the alternator, which is then transmitted to the distribution stations for domestic and industrial uses. The frequency of the induced EMF is given by F is equal to Pn by 120. And the direction of the induced EMF can be found by applying the Flemings right-hand rule. So in motor, it is going to be left-hand rule. In generator, it is going to be right-hand rule. Now let us see the rating of an alternator. Alternators are rated in terms of kilovolt amperes or megavolt amperes, just like transformers. So it is a product of voltage rating and current carrying capacity of the alternator winding. So the rating comes from the voltage rating and the current carrying capacity of the alternator winding. So if we take an example here, if the alternator is designed for 66 kV voltage rating and is carrying a current of, has the ability to carry a current of 100 amperes, then the rating is given by V into I. V is 66 kV into I. The current is 100 amperes. So you get 6600 kVA, kilovolt ampere, or which is also equivalent to 6.6 megavolt ampere. So it is just the product of voltage into current will give you the rating of the alternator. The capacity or rating of an AC machine, that is the alternator, is always expressed in kVA or MVA, and it is not in kilowatts or megawatts, because the kilowatt or megawatt capacity of an AC machine depends on the power factor of the load that comes on it. So here there is no question of angle power factor rising. What is power factor? It is the cosine of the angle between the voltage and the current. Since it is not a load, so it does not contribute the power factor here, and it is purely the rating is the product of voltage into current. The applications of AC generators, it is used for generation of electrical power. So you can see them existing in the hydropower plants, thermal power plants, and in the power plants. They are used in all types of generating stations such as hydropower station, nuclear power station, thermal power station, and diesel power stations. They are used for individual power supply when the power supply fails to meet the additional power supply demand. So that is the portable AC generators that you have seen. Alternators are used in modern automobiles to charge the battery and to power the electrical system when its engine is running. Marine alternators are used in yachts, which are similar to automotive alternators with appropriate adaptations to the saltwater environment. Then high frequency alternators are commercially to radio transmission in low frequency radio bands. So earlier these were used for transmission of Morse code and for transmission of voice and music. So these are some of the applications of AC. generators. Thank you. If you have any queries, you can